Dear colleagues, my name is Esmeryan, currently an associate professor at Georgi Nadjakov Institute of Solid State Physics, Bulgarian Academy of Sciences. It is my pleasure to attend for the second time the prestigious international conference on diamond and carbon materials, which unfortunately is held online this year. Perhaps many of you know that many carbon materials such as multi-walled carbon nanotubes, carbon fibers or graphene composites could be considered as a passive anti-icing tools. Unfortunately, the wide commercial employment of carbonaceous ice-phobic coatings is still at a bottleneck due to the scalability and functionality constraints. Currently, one of the research interests of our research group is related to the development of ice-phobic soot-based coatings, potentially applicable in cryobiology for naturally controlling the freezing and thawing rates during the cryopreservation of living matter, as it is shown on the following figure. There it is. So, one may obtain better survival rate of the living matter after the freezing and thawing rates using super-hydrophobic materials. This is a key challenge for the cryobiologist up to now. We use an inexpensive and single-step flame synthesis approach associated with controlled combustion of rapeseed oil at atmospheric pressure to obtain soot with divergent morphology, surface chemistry and roughness. We apply a secondary chemical modification of the pristine soot with alcohol and fluorocarbon in order to adjust the mechanical durability, the ratio of the functional groups and the porosity and thickness of the samples, as it is hinted in figure 1, which is shown below. So, the evaluation of 8 multifarious soot coatings under nearly 100 experimental cycles, the result of which are presented in tables 2 and 3. Show that the soot particle aggregate size, surface roughness and degree of non-wettability do not affect the ice-phobic performance of the coating. The film's thickness, air fusion arrangement and surface chemistry are the main parameters governing the anti-icing efficiency of the soot. In particular, the chemical bonds of the soot tailor its interfacial thermal conductivity and control the freezing time delay and freezing temperature depression. Finally, the occurrence of a new counter-freezing mode, which is shown on this figure here, so the occurrence of a new counter-freezing mode where the water droplet shell crystallizes simultaneously with the contact interface, as shown in figure 5, confirms our previous hypothesis that the cryopreservation of human seminal fluids via soot is successful due to gradual motion of the freezing boundary from the air-semen solid interface towards the liquefied bulk, inducing outward osmosis, suppression of the harmful intracellular icing and uniform dehydration of the cells. So as a conclusion, our results may complement the standards in designing ice-phobic coatings, potentially applicable in cryobiology, and emphasize on the relevance of surface chemical states, an aspect that is more or less overlooked so far. If you have any questions or find our research interesting, please do not hesitate to contact me via the email provided on the poster, or check my ResearchGate and Google Scholar profile. Thank you for your attention. That will be a second.